cells up to the M6 cell, 166 millimeters. And then like a year and a half ago or something like that, cells grew in size, and now panels use these M10 and M12 cells that are much larger. So in terms of panels, what that means is that we moved on from all panel manufacturers having the same size, either 2x1 or 2.1 by 1.05, to much larger panels. And not only that, but panels that basically took two routes. What we know today as the 182 panel that uses the 182 cell, and the 210 panel that uses the 210 cell. And within those cell sizes, we can actually find different panel configurations. So you have 1.1 by 2.2 or 1.1 by 2.4. And then this is on the 182 cell, as you can see here. And then you have three sizes that are using the 210 cell, which is 1.1 2.4, 1.3 2.2, and 1.3 2.4, which is a huge panel. So we moved on as an industry from something that used to be uniform and of a very round number of 2 square meters to a range of sizes that are currently available in the market. And that range is actually much larger. It's like 20 to 56% larger than what the industry used to be or was used to, right? So, but Arctech is a tracker company and a fixed tilt racking company. So I'm here to talk about the impacts that the panel change had on trackers. And then down the line, the impacts that the panel change have at the whole, PV asset level. Okay, so growing panel size means what for trackers? Well, it means that the trackers will be longer and also taller, right? So everybody that had designed trackers with specific dimensions in mind now had to revisit those designs because with a larger surface, all the wind tunnel tests that have been done had to be revisited, and not only in terms of coefficients that we use for stress calculations, for resistance calculations, but also the stability limits of trackers, because trackers are or have been flexible structures. Right. So the very first impact that these large format modules, brought to the industry was on panel capacity itself. So when the wind comes, and if the wind is coming from here, from the left, right, and we have like a traditional tracker, a flexible traditional tracker here that needs to stow at 30 or 45 degrees, because if it doesn't stow at the steep tilt, basically it will get unstable and eventually get big damage. So these trackers need to stow at a steep angle, but if you stow at the steep angle, this is the panel, the pressure profile that you have on top of the panels, which is pretty significant. Now, what happens if instead of 2 meters, you actually have these panels that are 2.4 meters, 2.4 by 1.3, 2.4 by 1.1, like I was explaining? This pressure profile is even larger, right? So everybody used to be familiar with, the old IEC, I'll spell it here, guidelines for load testing. And a number that everybody used to deal with are the famous 2400 Pascal of load capacity, of pressure capacity of these panels. Well, if the panels are much larger and you stow the panels at 30 and 45 degrees, you exceed these values. So these panels are just not, it's not possible to stow these panels at these angles without exceeding the IC guidelines. As a matter of fact, if you go to panel manufacturers, and if you have several EPCs and developers here on the call that are spending millions of dollars procuring this equipment, you go to the panel manufacturer, and a panel that is like 2.4 by 1.1 or even by 1.3, doesn't matter. You go to their installation manual, and they will have pressure limits that are way lower than this. So it's very typical to see these pressure limits reduced to half of what they used to be. The maximum I've actually seen is actually 1800 Pascal. So what the panel manufacturer is telling me is that, hey, listen, if you use these panels, which bring more power and eventually allow you to save some costs, make sure that the pressure, the wind pressure on that panel does not exceed these values. And I'm telling you, it's not possible to hold to these values. Most of the cases, if you stow the trackers at 30 or 45 degrees. So you may say, okay, let's not stow at 30 or 45 degrees, let's stow at 0. Yes, at 0, you are in the right because the panel pressure is much lower. So even if you increase the panel size, it will be still low profile against the wind, so the pressures are low. However, if you have a traditional flexible tracker with just a single fixed point in the center, you cannot stow at 0 because your tracker flies away. And this is what I used to call the tracker module paradox. If you want to protect your tracker, you damage your panel. If you want to protect your panel, you damage your tracker. So this problem had to be solved. And that's why we had to move on to a tracker configuration that could, for the first time, stow at 0 degrees. Okay? And one very simple way to do this was, okay, I just throw a whole lot more steel into that structure, and I make it much more rigid or much stiffer. But the problem is that nobody wants to throw steel in because throwing steel in increases the cost. So the whole point of doing large panels was to lower the cost. And here are the tracker guys actually putting more steel and increasing the cost. It makes no sense. So we had to revisit the tracker design and make a stiff design. Okay, and that's what I'm going to present here today. How stiff trackers solve those problems, and then add value to the equation. First of all, this is what I mean by a traditional tracker. This is what people have been buying and installing, and this is perfectly fine with modules up to the 2x1 modules, the 2x1.1. That's okay. But the definition of a traditional tracker is that they have a single fixed point right there. If you look at this animation, this is pretty much the behavior when the wind comes. Your tracker is, reflecting in the wind because it's a single degree of freedom structure, which is flexible. And it's more flexible as longer this half wing, as we call this fixed to free length. Okay, so with increasing panel sizes, we have increased this distance, right? This fixed to free distance and the chord as well, which increased deflection and lowered stability. And the problem with that? The problem is that we tracker people as tracker designers, we have no control of those dimensions whatsoever because these dimensions have to do with the panel itself. So the panel used to be like this, and now it is like that. So what can I do? I can do nothing about it. And then people kept the same number of panels per string, right? So if I put these larger panels one after the other, right there, this length is going to be much longer. So I have taller, like I said, and longer. And then I cannot do anything about it because I have one fixed point right there, and then I just stack panels one after the other. Okay? So what have we done then? What's the solution? Well, before the solution, I'm going to summarize the challenges of this design. First of all, if I make the tracker longer and taller, my tracker is losing stability. So the curve that you see right here in the right hand side is actually a stability map. And what this curve is telling you is this is tilt right here in the horizontal axis, and this is wind speed in the vertical axis. So it's, you cannot ever cross this red line. If you cross this red line, it means that the tracker starts shaking too much and flies over, basically. So you need to keep under this red line all the time. So before, we tracker people had this concept of operational wind speed. The operational wind speed is this that I've just drawn here, okay, which is is a wind speed limit. This is meters per second. It's a wind speed limit here that never crosses the red line, right? So after this wind speed limit, I put the tracker into stow mode. And stow mode in these traditional flexible trackers, as I mentioned before, needs to be at the steep tilt, okay? Now, what happens when this tracker grows in chord and length? Well, it's not the red line anymore. It's actually the black line, because the limits come down. The tracker now is more flexible because dimensions are larger. So these limits don't cut it anymore. As you can see here, this limit is now crossing the new stability line. So you need to come up with a new limit that I'm going to paint in red right there, that is actually much lower. So you don't cross the black line right now, okay? What this means here is if I have a lower meter per second, I used to be, it was typical that trackers used to be in this limit, the blue limit right here, with the older panels, the 400-watt panels, around 16. Some were at 18 meters per second. Now it's very common to see in the industry something along 10 to 14 only, right? So you have a limit at 10 to 14 meters per second. That means that after this wind speed, you must stow the tracker if you want to avoid damage. But if the stow threshold is so low, you are sending the tracker into stow very often. So if your tracker is in stow all the time, what's the point of having a tracker? Just put the fixed tilt. See what I'm saying? So it's not, the modules are larger to save money, but they affect the components around them, and they affect trackers heavily, okay? And this is the first thing that they do with trackers. The second thing we talked about, if you keep stowing these, your pressures are too high, and your limits are just not what the panel manufacturer is saying. And then the current trackers, these ones with the red line, used to have like a bunch of damping, which are very expensive components. And if we are designing a new tracker, we might as well actually simplify it and make stuff much more optimized. But the main two things that we must solve with stiff trackers are these two. We need to protect the trackers and prevent the critical wind speed, the stability wind speed, from getting too low, and we need to protect the panels, okay? All right, so how do we do it? Well, we do it with this stiff design right here. And this is a tracker that from the front, it looks like very similar to the previous trackers. But if you look from the back, instead of having just a single point in the center, has several fixed points along the torque tube. And this is what rigidifies the tracker, right? Because before, you used to have a fixed point right there, and then, a length of, a free length, a half wing that was doing this. Now, the modules have grown, and if you kept the same design, this length is not up to there, is up to there. So that's why the stability limits come down, okay? So we cannot afford this. We cannot afford this. So instead, what we are doing is we are putting several fixed points right there. And I'm going to show you without getting into very complex physics right here, but I'm going to show you right away how this thing improves. So let's see, in an old tracker, if this length used to be, let's say 45 meters, right? So it was a 90-meter tracker, which is to be very typical 3-string tracker. I'm talking about 1P now. So if this is 45 meters, right? So this thing here would be 45 meters as well, the same thing. But now the difference is that I have 30 meters here and I have 15 meters there. Okay, because I was able to put this thing right there. So the physical quantity that influences the torsional deflection is basically this tiny formula right there. So GJ over L. Okay, this is the torsional deflection right there. Okay, so G is a characteristic of the material, J is a characteristic of the cross section, and this L, yes, you guessed right, is this L right there. So the longer the tracker, the lower the torsional stiffness, which means the higher the deflection. Okay, so before I used to have a fixed point and a free point, a free end, sorry, right there. The distance was, this distance was 45 meters. That distance got reduced to 15 meters, right? So 45 divided by 15 is a factor of 3 times. Essentially, this tracker right here, the same dimension tracker, got 3 times stiffer by geometry alone, without throwing any steel at all, okay? Now, you may be asking, oh, how about a 30-meter fix to fix? Well, if you are constrained on both ends, this L is actually L divided by 2, because you have 2 ends. So you have the same 15 meters right there. So the whole tracker, no matter where you are in the tracker, is 3 times stiffer than what the original tracker used to be. Okay, so this is a concept. The beauty of this design is that we are solving stuff by geometry, and we as engineers, we like to have variables to optimize. So you look at this, and you are seeing like a 3 fixed points example, but we've done projects with 4, we've done projects even with 5. It depends on the wind speed of the specific location. Then you can actually get these posts, and you can move these posts to the left or to the right to tailor these fix to fix and these fix to free spans according to the project needs. In a traditional tracker, I cannot do anything. I have a central fixed point, and then I just stack panels. I have no control whatsoever. The good thing here is that I do have variables to optimize. And by multiplying by 3 the stiffness, I can for the first time stow the tracker at 0. And we've seen that stowing the tracker at 0 is paramount if we want to keep panels safe. And I'm certain that no developers on this call or anywhere want to go year after year to swap panels after the windstorm. No fun. Okay? Now, let's keep going. This is just a comparison. I won't stop. This is not the wind tunnel test webinar. I talked about wind tunnel tests in many other webinars. I'm happy to answer your questions after this if you want to take a look at that. But basically, what you see up here is a traditional flexible tracker, and you can see that the whole plant is behaving very differently. Right. So really quickly, if I stop this video, I stop this one. So take a look at these trackers. This is the external tracker, the exterior tracker that the wind comes. See, the fixed point is right there where my hand is pointing to, and the tracker turns almost vertical. The second tracker, though, stays at its original position. And then the third, the fourth, the fifth, they all have their own behavior. So all trackers are working differently here. And that's why these tests are very important, because it's not okay to make a wind tunnel test. Like everybody says, oh, I made a wind tunnel test. Okay, good for you. But people, some people, or some manufacturers make wind tunnel tests with a single tracker, and the single tracker is not representative of the whole plant. Because if you are studying just the first tracker, take a look at how it behaves. Now take a look at the other ones. See, I'm going to play the video, and you'll see that the first tracker, yes, it deflected a lot, but it's stable. It's not much. Take a look at these guys. These guys are going completely crazy. So this means panels flying away, posts bending, everything, while the first four were just fine. So if you are buying trackers from people that are showing you the first and the second, you are not seeing what's going to happen to your field. Okay. What rigid trackers solve now, these below our rigid trackers, is that the behavior is consistent across the solar field. I have these trackers shaking a little bit in the fixed to free, because the whole point of this test was actually to move the fixed point to the left and to the right to find the optimum equilibrium. You can see that the fixed to free ends are super stable. This is like at a huge wind speed, probably around 60 meters per second already. And we're having motion there because we opened the fixed to fix a little bit more. But better than me talking is like showing you the data. This curve right there, let me pause this so we don't get distracted. This curve right there I showed you before. The worst position for traditional flexible trackers is 0 degrees. So again, if you're buying trackers from somebody that is stowing the trackers at 0 to protect the panels, but they have a traditional flexible tracker with one slew drive only, you should question that, because 0 degrees is no good for these trackers. And this that you are seeing here is actually around 20 meters per second. So that's it. Above 20 meters per second, the tracker bye-bye. And I don't think that's what you're looking for. If you use rigid trackers, take a look at the curve. All of a sudden, the best angle is 0 degrees. It's a very stiff tracker. So I go from the lowest point at 0 to the lowest point at the steep angles. And the lowest point is right here because I decided not to use dampers. There are no dampers in these stiff trackers right there. And that's why it dips. But it doesn't matter to me, because even dipping, the wind speed is so high, so much higher above the operational wind speed that used to be 16, 18, that I don't care about putting dampers. Because if I were to put dampers, this curve would just be like that. But I am not interested in gaining this thing here, because my operational wind speed, if you remember the previous chart, is right there. Okay, so these are some numbers for you. And I want to expand on what that operational wind speed means. So basically summarizing one more time, why it's fundamental to have rigid trackers with large panels. One, you have the highest stability at all tilts, like we've seen in those two curves before. Two, you protect your panels. And three, you can generate more energy. So remember when I said traditional trackers used to be at 16, 18, now everybody's putting them at 10, 14? Well, we at Arctech are going in the opposite direction. Since we've stiffened the tracker so much, we actually increased the wind stow threshold. And we send our rigid trackers to stow at 22 meters per second. And 22 meters per second actually sends the tracker into stow much less often, which allows the tracker to actually collect more energy and make a better financial case for you people that have like PV assets. While if you actually stow at 10, 14, you are not collecting that energy. So that's basically the study that we have done. See, so this is the angle going this way. So this would be at 0, and this would be at 45 degrees. And these are the several wind speeds. And this chart here plots the energy losses for a specific case. I'm just making a point here, and now I'll show you the case. So if you actually stow, so what you really want is to be in the upper right corner which has like the least amount of losses, right? And the upper right corner means stowing flat and with a very high wind speed. Because if you stow at 45, 30, 45, and then at a lower wind speed, you're going to be throwing away a lot of your energy. And your energy, is basically what you need the trackers for, because you started by buying trackers to maximize your energy, not to throw it away. Okay, so we did like a case study in Amarillo, Texas, a 100 megawatt project, and we just compared two of our rigid trackers, Skyline 2 and SkySmart 2. This is our 1P and 2P that's still at 22 and 20. And then we have like the traditional flexible trackers that we are calling A, B, and C. That's still at 16, 14, and 12. And again, what people are doing large panels are, the 12, the best case probably at 14. Okay, so we got all, for Amarillo, Texas, we got the solar radiation and wind data for that specific site. And, this is the plot of the whole distribution of wind speeds, the hours, and what you see here is the intervals in meters per second of the wind speed. These are intervals of 1 hour averages, okay? We use the thirst curve to turn the 1 hour into a 3-second gust, which is the duration of gust that we use in tracker design. And basically, the way to read these is the following. Okay, if I have a very high wind stow threshold, which is this vertical line here, I'm only losing everything that is to the right, which is very, very low. It's just the tail of the distribution. On the other hand, if I have a tracker like a tracker C, this one here, that stows at 12 meters per second, and 45 degrees, I am losing all of these events, right? Because, there are still many hours where the wind speed is higher than my threshold. If when we have these hours, we also have solar radiation, you're not collecting energy. And that was the whole point of these exerciise. We actually wrote a very nice white paper on it. I've got the link here. Then if you want to download the white paper, it explains the whole methodology and you can see all the details, but I'm going to explain them briefly here. Okay, so basically, if you stow at a higher wind speed, the amount of hours that I lost for this site were only 15 hours in this year. While, Tracker B actually lost 600 hours, Tracker A lost 200 hours, Tracker C lost 1,300 hours, okay? Means that this guy has been 15% of his time in stow mode. Again, I ask, well, what's the point? If you want to be in stow mode, just like use fixed tilt, Anyways, so how do we calculate the energy? Because now that's only wind, and now we need to bring solar, the radiation into the equation. So what you can see here is that this orange line is the energy that you produce using a tracker. This is an example for a specific day. Then we actually ran these numbers for every single day of the year. Okay, so if you are tracking the sun without ever going into stow, you just produce this energy. The energy would be the integral of this curve, basically the area underneath this orange line. Okay. Now, if you are, the green line, the black line, and the red line, the yellow line are lines for fixed tilt. This is a fixed tilt facing east, the green one, and this is a fixed tilt facing west. Of course, it collects much more sun when it's facing the west, and this is a fixed tilt facing south. Okay, right? So you understand that. So basically, in our exercise, when we said, okay, when the tracker is in stow, we default it to the fixed tilt line. Okay, because that's basically what the tracker is. It's a fixed tilt. Okay, good. So now it's where the fun begins. So this red line right there is our wind stow threshold. So what you can see here is that, since the wind speed are these bars, these columns here, the gray columns. So since my threshold is above all incidences of wind speed, I generate 100% of the energy. I did not go into stow, not even once. Okay? This is the curve. This is what happens for 22 meters per second. For 20 meters per second, the same thing. Now, what happens if I keep lowering the threshold? I've touched some of the incidences in the afternoon were higher than my wind stow threshold. So I had to send the tracker into stow for a little bit. So I lost the differential between this ideal line, which is the blue line, and this orange shade. So basically that blue shade right there is loss that it was caused to me because I went to stow, into stow. If I keep lowering the threshold, I will have more and more losses, right? This is a tracker B that stows at 14, and this is tracker C that stows at 12. You see? So basically, we computed these two, these 5 trackers, all days of that year for 100 megawatts in Amarillo, Texas. And here you can see the figures. And just to make the comparison a little bit simpler, I'm comparing our rigid 1P tracker 22 with a common 1P tracker in the industry that stows at 30 degrees and 14 meters per second. And basically, this is the flexible tracker that is stowing at the highest now, because everybody's like below this. And you can see that while stowing at 22 loses 0.09%, this guy here loses 1.68%. That in terms of megawatts is about 3,500. Okay. These are numbers that maybe don't tell you much, but what I'm trying to, I'll give you another perspective to try to make you understand what these numbers mean. But before that, I'd like to present this chart because this chart tells the whole story. Okay. So basically, this is wind speed right there, 12, 13, 14, 15, 16, up to 22. And this is the energy loss. And the several colors is tracker tilts, the tracker stow, right? So for instance, our rigid trackers that stow at 0 degrees follow this blue line. Again, I can only stow at 0 because I have a rigid tracker. Do not stow a flexible tracker at 0 because everything will go bye-bye. Okay, good. So if I follow the blue line because I can be at 0 and I'm at 22, I lose just a little bit, almost nothing of energy. However, if I stow at a steep angle and a very low wind speed, I can lose a lot of energy. My example was 168, but if you go like with the industry trend, which is 12 and even 10, you can lose like 4 or 5% of your energy available. And that's a lot. And again, lots of numbers. I'm going to be quick with this message because there are some developers on the audience that probably understand all of these financial figures. But the main idea here is that if I generate 1%, 1.6% more in terms of megawatt hours, this is energy. Okay, that's equivalent to $3 million more revenue after 35 years. This is a typical, very typical project life in the Middle East, in the USA, where this comparison was done, and that's equivalent to an IRR of right. So if you stow higher, you have an IRR that is higher by 0.168%, and maybe this number doesn't tell you all much. Nor the NPV, which is like $1.2 million more. But if you flip the question around and you say, okay, wait, I get it. So if you stow higher, you generate more energy, which gives you a little bit more IRR. But is 0.168% really a lot? Well, let's do the opposite exercise. So let's get this tracker B. Okay, and let's say, okay, how much lower this cost had to be So my financial performance was the same. So my IRR was the same, right? So here I'm comparing, okay, I have our Skyline 2 that stows at very high wind speed, and I have this tracker B in the industry that stows at less, it generates more energy. Sorry, this one generates less energy, which means that this IRR is less. But if I wanted this tracker to have the same IRR, I need to lower the cost of this tracker. And I generate the same IRR, see the differential is zero there. That means that the cost had to go down by 1.3 cents a dollar. Again, your upfront costs for your tracker purchasing would be 1.3 cents, would have to be 1.3 cents lower. So the value that stowing at 22 meters per second in 0 degrees creates is 1.3 cents of US dollars in tracker acquisition. And this, in today's tracker cost, is probably around 15%. So what I'm saying here is that the value I'm creating is equivalent to 15% tracker upfront cost, which is probably easier to visualize than 0.168 IRR. Okay. Anyways, I've been talking for a long time. I'm almost consuming the hour, and we still have Satish that needs to talk after me. So it's just saying that we ran several locations as well, and just quick summary and conclusions here. So the main point is that traditional trackers that do this a lot are getting obsolete with large panels. So be careful if you have your project with large panels. Be careful in terms of the tracker you're buying. If you use these large panels, you must stow at zero, but you can only do that if the trackers are rigid. Because if the trackers are not rigid, one of two, your stow threshold is so low that you are in stow all the time, or you will get instability problems. And finally, if you have a rigid tracker that can stow higher, at a higher threshold, you get more energy generation. And I've just told you that in our 100 megawatt Amarillo, Texas project, that was equivalent to 1.6% more energy, which is basically 1.3 cents a dollar of upfront tracker cost value. Okay, and all of these calculations are explained in this white paper here, which you can actually go and download. You just click this link, or type this link, and you can download this thing here. And all details are there, and I'm always available to answer the questions you might have about that. Okay, so Manif, I'm gonna hand it over to you.
Thanks a lot, Pedro, for this informative session. You indeed actually triggered some discussions here in the chat. Thank you all for your input as well. I'd like to mention Stavros, Jihad, Dr. Mohsen, Khalil, and please send your questions in the Q&A section so we make sure that we would answer these questions together with our panelists today. So I'll move to the next section and hand over to Satish, please. If you take over from here for the coming, let's say, 10, 12 minutes, and then we move into the Q&A session at the top of the hour, please.
Thank you. Thank you, Mani.
Thank you. I'll let you know when we can see your presentation. Okay, it's in full screen and visible. Thank you.
Okay. So myself, Satish from the Mahindra Teqo. We are the technology-enabled renewable asset management company, which look after digitalization of the renewable platform and taking care of the operation and maintenance and some due diligence, special kind of services to enhance the solar asset. So we'll move to the next slide. So basically, we belong to Mahindra Group, which is like 20.7 billion group company and present across all over the world. However, we operate currently in the region India, Middle East, Thailand, Canada, and some part of like Europe as well. Now, so Teqo play a 360 role in the life cycle of the PV project. So first, we do technical due diligence, and here we generally provide the evaluation of the asset during the construction, during the operation and period, and during the financing of the refinancing of the project. And project management. So project manager basically belongs to the testing and commissioning during the construction of the project. KPO services, owner's engineer, then operation and maintenance and asset management. Currently, we are operating a portfolio of 6.2 gigawatt in India, and in digitalization format, we have our own SCADA and advanced analytics platform, which helps to monitor the plant in a way such that we can like indicate if any kind of like a failure or something like it's going to underperform. So we, through the digital platform, we trigger the things in a well advance through like a real-time monitoring through the central monitoring system or CMS, then advanced analytics, remote monitoring. In remote monitoring, currently we are like operated approximately 10 gigawatt plus. In that, this KPO services basically belongs to one of the projects which we are operating in the Canada called like real-time monitoring and giving the insight on the daily basis or sometimes a real time as well. So at the end of the day, we will summarize all the findings and share with the our respective clients. Then intervention services. Here we generally customize the services during the operation of the project such that it will increase your ROI. Like, so if the project is at 10th year of operation, then we will do technical due diligence of that project and try to make it this project such that if we can compensate the degradation or some like other net like a defect which are like prone to with respect to the time. And we do like a factory audit, PDI, lab qualification as well, so that like sometimes like a investor or the owner can have a confidence on the module which they are procuring. And another one of the key USP, we do on-site testing. So our this mobile PV lab is the first in India. We developed this, and now currently we have covered approximately 84,000 kilometers with 10 gigawatt of asset coverage while doing the module testing. So these are the like few points which I'm just taking this, so like underperformance detection, this will help to the reduce the transportation and handling charges, and not only the handling charges, that will minimize your like minimize your risk on the testing side. So like during the transportation, you have sent some good module, but during the it got damaged. So your like test results are not as expected. So maybe that deviate your the whole result. Similarly, minimize your generation loss. So you can do the testing during the non-generation time, and you can connect those modules again in the plant so that it can generate it. Another one is the AC testing. We do generally HT panel transformer switch yard, and this a la carte is such another like tool which we do with the help of a mobile lab as well, like qualification of cleaning robot and ARC coating and albedo measurement as an additional tool which we have in our mobile lab, so that we can do as a like a 4 hour per day albedo measurement that will reflect your entire area where you want to build your bifacial based solar plant. And these are the key tests which are like generally like 80% of the time we do. flash test, electroluminescence, drone thermography, as well as handheld, and the paranometer data validation, because it's a very key measurement parameter to understand your plant is performing up to the mark or something, like we have take a necessary or corrective action depending on the time to time. So this will help you to understand your precision or accuracy of the measurement of plant performance. And now moving to the core, which we like in the webinar we have working on the tracker front. So based on the tracker and my experience, I have done approximately 8 to 10 gigawatt of the project based on the tracker, and found that the GCR have a very strong correlation. So here, even though actual versus your estimated numbers may vary if we increase the GCR. So suppose, for example, if we are considering the GCR of 0.5, then suppose your estimated energy is X percentage over your fixed yield. So during the actual scenario, your actual is X minus some Y percentage. However, in the range of 0.34 to 0.42, the gain is almost same as the estimated one. So this green region shows that the appropriate selection of GCR, as this will also help you to adopt your concept with inner row versus outer row, because if you lower than the 0.34, so then again your other losses will increase, like DC ohmic losses. So considering that one, this 0.34 to 0.42 is the optimum for across the 90% region where trackers are feasible. Now, in terms of the bifacial, if I'm just focusing here for the bifacial front with respect to key optimization. So rear side setting, if we increase from 0%, like there is no shadow, then increase your generation or the yield will drop by 3.2% by every increase in the rear side shading loss. So in next upcoming webinar, maybe I can explain how to calculate the rear side shading based on the torque tube, shape and size of the torque tube, and the height between the torque tube and the module. Second one is the height above the ground. So it's again have a strong correlation here. It depends on the 1P configuration or 2P configuration. If it is a 1P, then your height will be recommended height will be 1.8 to 2 meter. It's the optimum height. For the 2P, it's a 2.6. Similarly, for the rear side mismatch loss, it's again depends on your other factor, say bifacility factor, height, and the albedo. So here the considered this mismatch loss, we try to derive some number based on the assumption, like albedo is 20%, bifacility 75%, and the height is 2 meters. Then how your rear side mismatch loss varies with respect to your these parameters. So another front which are not depends on the tracker, but that is impacting your the bifacial yield, all called these albedo and the bifaciality factor. So albedo generally in desert area we get between 0.28 to 0.34 approximately. So these numbers are strongly correlate your bifacial this energy yield number. Then bifaciality nowadays your for the mono perk you are getting 75%, but for the guarantee purpose maybe it is lower. So you can take a tolerance of 2.5% as a bifacility factor while doing your simulation. So if if the module manufacturer are guaranteeing you the 75%, then you can ask what is the tolerance of that one. So maybe some manufacturers say 5% tolerance you can consider. Some manufacturers, no, we guaranteeing minimum 75%. So you can take an average 2.5% as an additional. So while inputting in your yield estimation, you can take a 77.5. Moving to the next. So in terms of the a selection of tracker, you have to think as a 360-degree, so that you can capture each and every aspect. So that will give you the best ROI and the lowest LCOE. So it like bifacial is not only depends on the one factor or like some two factors. So here multiple factors are involved. So another there is a one experiment performed to understand the shadow effect on the rear side. So by doing this study, we like this paper has considered like one paranometer at the center of the module, another one at the both the edges, east and west. So based on that, during the day, it was found that the loss in this range, 500 to 1000, when the radiation is higher, your rear side shading loss is 3.96%. So in terms of the considering the yield loss overall year basis, it goes around 0.22%. So this is for the circular. Maybe for the square tube, this loss may be slightly higher. So we are working on that. Maybe in next webinar we will have that result as well. Another interesting thing in terms of the bifaciality gain. So this gain depends on your irradiation values. So during early morning or late evening, you can get the maximum bifacial gain. However, your generation is lower, but your bifacial gain is higher. So by this result is published by the NREL with the experiment of setup of 75 kilowatt with the tracker, and it shows that your gain, average gain is approximately 6.82, some around 8%. Again, it depends on the albedo. So here albedo was approximately 25%. So if you see on a day basis, if you want to compare how your gain is varying on a day, so you can see early morning your irradiation is approximately lower than the 200 watt per meter square irradiation. So early morning and late evening, you can get the maximum bifacial gain. And slowly when the radiation increases, your bifacial gain slightly going to the down because of this tracking profile. And another result based on the technology. So here two technology results was compare silicon heterojunction and PERC. So based on these results, here it's compared between the temperature and the bifacial gain. And the second graph, which shows that the estimation with the two tools, SAM and the PBCist and measured data. So based on this result, it was clearly found that these simulation tools are underestimating bifacial gain. So in for this case, HIT shows 9%, PERC shows 6.5%. However, when the overall these tools are estimated for the SAM, it was estimated approximately 4.5%. PBCist estimated in the same range, within the 5%, I can say here based on this result. So what happened? We can say some losses or some assumption with respect to bifacial are still under evaluation to get the appropriate numbers to match the actual number. So most probably one of the major reasons how to measure the actual albedo and how to translate that albedo into the energy number. So second one is the rear side view factor calculation. That is also one of the key factors. So these two areas are under evolving, and maybe soon we have a better simulation tool. And there is another simulation tool developed by the NREL. They are using, and they are claiming that they have a like 95% confidence interval. They got the result highly correlated with the actual. So sometimes we can explore, but that's like a lengthy process, because that give you some factor and then use that factor to your some other tool like SAM and PVSys to get the final yield number. So thank you.
Thank you, Satish. This is very informative. Indeed, these are a couple of, let's say, very good tests and studies that you have done and you have shared with us that also would be helpful to complement the knowledge that we got today. And I've got also a couple of questions for you. I think we are a little bit over time. I'd like to ask the attendees to bear with us for 5 more minutes, just at least to answer like 3-4 questions before we end the session. I've seen, Pedro, that meanwhile you answered the questions of Mustafa, Stavros, and Khalil. If you guys find the answer satisfactory, and that's great. If you have a follow-up question, then please ask it, and then we go ahead with it. First of all, I wish to ask Pedro, because there's this kind of feeling when we're talking about stiff trackers that we mainly think about or focus on the, let's say, reliability of the system just to make it stronger and so on. But your presentation was full of other indicators, which are more towards energy and IRR. So would you please just comment on this, please?
I was on mute. Sure. Right. So the very first motivation for stiff trackers was actually to protect the assets. Mm-hmm. And it's, I talked about the module and tracker paradox. We must protect not only the tracker and put the modules at risk. We must protect both things, and that can only be achieved with rigid trackers. That's okay. But mm-hmm. Once we have a rigid tracker, we can actually capitalize on the value of having a rigid tracker, because rigid trackers enable more energy production. And that's what actually people need to see beyond, right? So if I'm bringing value to the table, I am making, I am allowing you for a better financial case, right? Which is the reason why people use trackers to begin with, because otherwise people will just put like fixed yields and forget about value. So yes, reliability is, top priority. But then once you got that solved, it's very important to focus also on value creation. Okay. If you allow me, there was one question that was very pertinent that I did answer, but I can see that I was not very clear in one thing, which I think it was Stavros' question. Stavros, saludos, review. Right, so Stavros says, okay, traditional trackers have one slew drive, and now you all of a sudden, in your example, you put 3. But then in your financial case, when I presented the tables, both trackers start at the same cost. How is that even possible? Because if you put more drives, more mechanisms, your tracker must be more expensive. Right, so this is a good question. And I think we ought to take like 30 seconds to talk about this. In a traditional tracker, first of all, the slew drive that you have in the center is much larger. You know why it's larger? Because, see, the moment diagrams of that tracker are just like that. So this is the amount of moment this huge slew drive in the center sees. Take a look at my tracker right here. So I'm actually dividing that moment into 3 fixed points. So I do not have a 9 or 7 inch slew drive anymore. I have 4 or 5 inch slew drive. So the size of the slew drive is much smaller. This is reason number 1. Reason number 2, this tracker here is designed with a steep angle, with that huge pressure profile. So all steel components underneath this pressure need to be much beefier than this tracker that only has this tiny pressure right there. So these posts are much larger. These tubes are much larger when compared with these ones. So the quantity increase here, quantity goes up, but size goes down and steel goes down. When we make this trade-off, this tracker right here is cheaper, not more expensive than this tracker, mainly in high wind regions, because it's very stiff. And in high wind regions, this tracker here needs to go huge in terms of steel component. Okay, so I felt that I did not explain that in my presentation. Sorry about taking
Perfect.
But I think it's important.
So at the conclusion, this outweighs the additional cost. So basically, your tracker would be at the same price level of a regular, let's say, 1P tracker.
If you break it down, my drive cost increased a little bit because now I have 3, although smaller, I have 3, but everything else in my BOM decreased. So when you put everything together, the overall tracker cost is lower or the same in very low wind regions.
Perfect. Thank you for that. That is very helpful. I want to move just to Satish just for a question, and then we get back to you for a final question, please, Pedro. Satish, I think what caught attention the most among the participants is the rear shadow of the 1P trackers. Yeah. So in your assessment, does this outweigh the benefits of the tracker or not? And if you just also kind of tell us if that's more specific to the 1P trackers, because on 2P trackers, I think the impact is reduced because the kind of that structure is in between the panels, or is that a wrong assumption?
Yeah, so yes, definitely tracker makes more sense compared to fixed field for the bifacial case, because in tracker, your rear side shadow loss is much lower compared to your fixed field. So it approximately based on this Arctech tracker with that kind of arrangement, this rear side shadow loss as an input for the energy yield assessment is ranging from 6 to 10%, with the albedo around 25 to 30% of albedo.
Okay, perfect. Thank you for this. I hope this answers the question for Ihsan ul Haq and the others that also asked this on social media. And I get back to you then, Pedro, as just like one last question. So then we can comfort, I think, the people that with the move towards this bigger form factor of the PV modules, that the tracker technology has caught up with that change. And there is, let's say, advanced technologies in there that would help make the best out of these assets, to protect them, first of all, and to also increase the energy yield out of these modules. So how do you see this kind of developing forward? Like what is next? Just to give some excitement to our audience before we end this session, to expect a little bit like what kind of change to expect for the tracker industry in the coming 2 years.
Well, I wish I had a crystal ball. No, but I like I said, we are working in the next step as well. The very first thing I'd like to say is that it's a good thing that now the industry, at least the players, the suppliers of the major components are I see working more and more together. Okay, so I do have frequent calls and meetings with the engineering managers of panel companies, inverter companies. So we actually, as you said, catch up on what everybody's doing and prepare our products to be the best as a system, because developers, owners that want to put up PV assets, they don't really care if the tracker is super optimized, if the panel or the inverters are not, right? So we need to optimize everything as a system. And it's good that at least on my side, I can say I'm meeting with my peers that work on inverters and modules to make that happen. Now, about the trackers, you take a look at trackers today, and trackers today have been, these single axis horizontal trackers, one torque to many posts, and panels on top. And we've been seeing trackers like that for 20 years. Right. So, that was the architecture. That's one, if you want, the optimization studies done 20 years ago, when the industry was at a lab level, when we were like 10 people working on trackers, so to speak. I say that today we are revisiting, and I think there are other people revisiting other architectures that were discarded 20 years ago because they did not make sense back then. But remember, back then the modules were at $6 per watt. The inverters were, like string inverters of like 100 kilowatts. So the industry has changed so much that maybe what did not make sense 20 years ago, certain concepts will make sense today. And I think that not only trackers, but panels, inverters will move on capturing more and more value. It's not only about cost down, cost down, cost down, cost down, which has been the trend for the past 10 years, right? So we're getting to a level where I think the winners will be the ones that provide more value to the customer, not necessarily always the lowest cost.
Perfect. Thank you for that, Pedro. I'm really happy and excited from what I heard from both of you. So we're like from your side, Pedro, as manufacturer of solar trackers, you explained to us how trackers are getting better and better, providing more and more value, but for the same price level, so we don't penalize the customers at the price. And also we've seen Satish and how Satish and his team are doing these studies and analysis to see the impact of these new technologies on the performance of PV plants and how to optimize the generation of PV assets. So again, this was a very informative discussion as well. So I thank you both for this very informative session. I would like to thank all of our attendees today. I know that it has coincided between Ramadan in the Middle Eastern world and then the Easter holidays as well, but still we had a very high turnover today between Zoom and social media. Very happy to have you on board. Thank you for your time. I hope you found this session informative, and we promise you to get back again this year with another session where we would go one step forward and learn something more about the very fascinating tracking solutions that are being developed around the world. Thank you very much and wish you all a very nice day. Have a day. Bye-bye.